Hi, you're welcome to You Know Nothing About Server, or You Know Nothing Server. I swear this with a comma, about encrypted messaging. This is actually my first conference talk, so be gentle with me. Thank you. Hi, I'm Jameson Lee. That's my Twitter handle. Follow me. I work at a company called TrueVault. We are a secure data storage API as a service. Right now, we do HIPAA compliance. If you know what HIPAA compliance is, then you're in healthcare. So let's talk about encrypted messaging. So why do we want to talk about encrypted messaging? Well, it's because it's a hard problem. It's so hard that there's a lot of money involved. But I don't think it's that hard. I don't think. Quick disclaimer. I'm actually not in securities. I'm actually in ops. And you probably shouldn't trust everything I say. End of disclaimer. So, let's say you have a super secret business plan. And you're pretty busy. So, you're busy. You can't quite, always trust the way you communicate with other people. And you don't know, some people may be snooping at things that you do. So what do we do? Well, this is a classic crypto story. Meet Alice. Alice likes to talk to Bob. Alice and Bob wants to share their super secret business plan. So they can just talk, right? No, that's not how you do it. Every time Alice and Bob wants to talk, you know who's there? That guy. Who do you think is holding the phone? So how do you do it? Well, we can encrypt everything, all the things. So there's many ways to do crypto. Common ones that most everyone hopefully is familiar with. Hashes, like HMAC, with SHAs. Symmetric encryption, like AES. Asymmetric encryption, like RSA. And hybrid, which is a mix and match of a few things. We're gonna go over using asymmetric encryption. So what is asymmetric encryption? Asymmetric encryption is using generating a private and a public key that you can use. You can publish the private key all you want, and the public key is used to encrypt any and all sorts of data that you can and anyone can send to you. And you can use the private key to decrypt it. So as long as you keep your private key safe, you can send the private key to anyone. So you get a private key, 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 everybody gets a private key. All right? But you do have to choose your asymmetric algorithms correctly. So there's a few choices. There's more than this. I just got tired. I personally prefer to do RSA. But then also after you choose a cipher, you also have to choose the length. The minimum length, everyone should remember, is 2048. Anything less than that is no longer allowed. Like literally not allowed. So there's all sorts of ciphers. We'll use GPG in this tutorial. GPG is the Gnu Privacy Guard, which implements the OpenPGP. PGP stands for pretty good privacy. It's pretty good. That's the manual if you want to go read it. It's a good read. OpenPGP is a hybrid cipher, which means it uses both symmetric and asymmetric encryption inside. So how will we do this using OpenPGP or GPG? So Alice can now encrypt the message using Bob's private key. Then Alice can store the message on Charlie's server. Then Bob can come by anytime, pick up the message from Charlie's server, and Bob can just decrypt the message using his own private key. All right, this can't be that hard. And it isn't. So here's a Flask server. So hopefully a lot of people are familiar with Flask. So all this right now does, starts a Flask app. Then this is the model for the message. And it's pretty simple. You have an ID because I'm using MySQL, and you have to have an ID. Recipient, which is the person you're trying to send the message to, and the message body, which would be an arbitrary string. And a little bit more. And you only really need these two methods. So you need to be able to put a message onto a server and to be able to get the message back from the server. Discarding all sorts of like error checking, by the way. And this is a client. All the client has to do is know where the server is, have its own GPG key, be able to send a message to the server, and be able to receive a message from the server. Very straightforward. There's little util methods like get or generate GPG or self-encrypt. I'm going to skip over the get over generate GPG because it's literally calling GPG and calling generate. So here's the encrypt decrypt method. Again, very straightforward. GPG library with Python, the Gnu PG provides all these methods just out of the box. So all you have to do is send it a message, who you're sending it to, your signature, your passphrase, and it encrypts it all. So again, I'm not a crypto guy. I just know how to use these ish. So this is great, right? We're done. No. There's slight issues. We actually don't know who the person sending the message is. We also don't know who you're talking to. So we need to verify the identities. We need to verify the identities. So you would ask, why do you need to verify the identities? It's encryption, right? It doesn't matter who gets it. Well, sort of and sort of not. So if you're just assuming that you're talking to a server all the time, it's perfectly fine. But when you're not talking to a server all the time, it's not perfectly fine. So identity verification is very important. So how will we do identity verification? So I came up with a very simple scheme. If you're a user, you contact the server using the server's private key, public key, encrypt a random string, and tell the server, ask the server, are you the server? Server responds with the key that you sent, and they encrypt a message with your public key, and they say, hey, are you the user? Here's the key you sent me, and here's another key. Then the client and server can just encrypt the message back and forth using the new key that the server generated, and some scheme that you agreed with, and just communicate, right? Easy. And everything's done with the new key you generate. Anyone familiar what this actually is? No. Even simpler. This is just the SSL handshake. Hello, hello, hit the key, and let's talk using the key. So let's reinvent that wheel. All I have to do, I add these authenticate and this challenging. So authenticate just tries to see if you have a secret, and if you're in a session. If you don't have a secret, generate a secret to share. If you haven't challenged the server, which if you haven't succeeded, you would have a session, you challenge the server. Otherwise, you just return the secret and go on with your life. So the challenge server method, again, just calls the server, attempt to authenticate, and does exactly as previous slides showed, was asked to send a key, your secret key, gets a response from the server, parses a secret key from the server, verifies that it is indeed the key that you sent to the server, then you use the new key from the server to use in your session. On the server, equally as simple, just need an authenticate method. Decrypt the message from the client, make sure that you can actually get the key, pass the key back to the client, and you're done. Easy. Very easy. No, not quite done. Sorry. There's a few things we skipped. If you go to the client code, there's this little thing where we have the server's key, server's public key. How do we get that? I hard-coded it. I'll have the client, or that was the client. How about the server? Well, how do we know who the client's fingerprint was? Well, also hard-coded that, which is the second part of the question, who you actually are. Well, that's actually about identity distribution, which there's actually many schemes. If you look at SSL, there's one scheme, which is the PKI, the public key infrastructure, where you have the CA, the RA, and the VA. The CA is the certificate authorities, RA is the something authority, and then VA is Google, if I remember correctly. But mainly, you have to pay the CAs a lot of money so they can keep the certificates. But do you trust those people you're tossing all your money at? Maybe. The other scheme is it's called the Web of Trust, where you directly trust people in a small network, and hopefully you can build out your own network of trust, and eventually that'll flourish, and everyone will trust somebody in a large network, and hopefully that network grows out. They both have their problems. At the end of the day, I prefer Web of Trust over PKI because Web of Trust is free, and PKI costs money. But as a company that I work for, we like PKI because we pay money. So Web of Trust. With GPG, and this is the reason I picked GPG, is there's well-known servers who host identities. So two very famous ones is the MIT PGP server and the PGP company who host the servers. So this is great, right? There's two very authoritative servers you can get your people's identities from. Well, I may not trust that server. Also, these are over HTTP, so really not trusting these servers. So you know what? I'm going to run my own server. Well, somebody else probably going to run their own server. Somebody else probably going to run their own servers. So we have a lot of servers with a lot of identities distributed across a lot of places. Best way to deal with all of this, get a pool going. That's a pool, I think. So this is a relatively famous pool, the SKS key servers. There's a wide variety of servers, and the MIT server and the PGP server, they all use this to synchronize keys. But now since I can join the pool, you can join the pool, anybody can put their keys into the pool. That's not a really good pool. Then you can put anybody's identities, and it's not a great pool. Like, it's not really a clean pool. That's the best we got. There's actually a new player in the ground, a new player in the field called Keybase. They actually do something slightly different. They do identity validation via your web identities. So they no longer try to prove who you are as a person, which is what the usual case with GPG is. Instead, they say, are you this person who claims to be this person on Twitter, GitHub, Facebook, Bitcoin address, Coinbase address, website URL, DNS, and a few things. So instead of trying to prove who you actually are as a human being, you try to create your identity as a web presence. So you could be a robot. But it's great, because at least you know that is the same robot all the way through. We can also build this key server. Pretty straightforward again. We create a new model called the public key. This has, again, very similar to the message, a fingerprint, which is the fingerprint of the user, and then the public key itself. And we just do two little things. Allow you to add a new user and also to get a new user keys. Pretty straightforward. And that's it. Very easy, I think. So what did we do? We got Alice sending messages to Charlie's server, and Bob being able to retrieve message from those servers. We secured their identities, so that was good. And we were able to distribute their identities through a large pool. All of that for this crypto messaging server that you could run to power your secret sharing apps, your super secret enterprises. 256 lines. That's all Python. And the best part, completely anonymous. Because the way we did it, there's no user models, there's no emails, there's no identities. Every time you want to trade messages, just create a new key. Upload the key to the server, send messages back and forth. When you're done, discard the keys. Don't actually know who you are. But you can always claim your identities back if you have the keys. So here's a little short demo. Hopefully that works. Where does this go? Go to the right. Okay, so on the left is the server, which I will now start. So the server is now running. This is the exact code that's on the that's been in the slides. And before I should go forward, am I in the right directory? No, I'm not. Before I go forward, I'll show the client file. The client, same code. A client, all it does is starts a client, attempts to get a message, sends some messages, and then retrieves the messages sent. It's not a very complex client. Oh, this is a secret path. Don't look. Don't worry. I generate this passphrase every single time. So what we see on the server is the client authenticating, then receiving the message, receiving the authentication handshake. Then we attempt to get a message for ourselves, which there's obviously nothing. Then it posts a new message, and the server says okay. Then we attempt to get our message back, and we get the message we sent. And that's it. So last thoughts. Somebody mentioned Diffelman. Diffelman is about forward secrecy. Forward secrecy is about every session you have has a newly generated key, such that if you ever compromise a single session, you cannot compromise a session in the past nor in the future. We actually do have, GPG actually does provide that in a sense where with GPG, every GPG message you send, you encrypt, is, as I said before, it's a hybrid where the message you send overall is encrypted with a public key, but the message inside is actually encrypted with a symmetric key. And you just send the key and the message together. The nice little thing about that is this thing called plausible deniability. If anyone ever compromises a message, then you can say, well, the message you compromise, which you have said you have decrypted, includes a key which you can use to recreate more messages. So it's a little popular thing where if you can see the message, then you can no longer use that message in an admissible way to prove that it was you who actually sent the message. It probably won't hold in court, by the way. Some cool stuff you can look up after this. DNSSEC, which allows you to do SSL, basically SSL and cert pinning at the DNS level. OTR is basically what I just did in whole. And there's IOTR exists as a library. PFS, which is the perfect for secrecy, which is the complete cycle of key dumping and the message and everything. The GPG internals is actually quite interesting if you want to read it. It's actually a pretty short read. One of the things, a MFA possessions factors is a talk from PyCon earlier this year, if anyone's seen it. It talks about how you can actually verify the user is who they say they are, and I can make sure that who they say they are is the person they're saying, and they need to prove to you who they are by multiple factors. The factors being the knowledge, the access to the keys, the knowledge of what the keys, knowledge, which is the password, access, which is a device, and then sessions, which is a time limited and authenticated. Last thing, don't go around signing random keys. Just sign my keys. No, don't sign my keys. The source of the code is on GitHub now. And thank you. All right, I have 5 minutes for questions. Do I have questions? All right. Thank you.